In this video, we're going to look a little bit closer at electric fields. Specifically, we're going to look at something called electric field lines. Now, what we saw was that an electric field, let me just write this equation down again. An electric field is going to be some electric force divided by some test charge Q. That's just some little charge close by the other charge, capital Q. So let's take figure A here. This is going to be our charge Q, capital Q. The electric field is going to be KQ over R squared, capital Q. And the electric force then would be some little charge Q times that electric field. Now here's how to imagine the electric field. Also, another way of thinking of it is a field of influence. Let's take some charge Q and just place it anywhere. We're going to say it's a positive Q. Let me write that down here so you can see that better. There's a positive charge Q. Since it's positively charged, what's going to happen to that test charge? Since they're both positively charged, they're going to repel. If I put that charge here, what's going to happen? It's going to repel. If I put that test charge here, it's going to repel. So you can see why we call it a test charge. We can move it into different places to test and see what's going to happen to that charge. So no matter where you put it around this positive charge, you are going to have, the test charge is going to be repelled or pushed away. And so we draw these electric field lines always pointing away, because that's what would happen to a positive charge if it were placed near it. Now let's go to the negative charge in figure B. So now we have some charge capital Q, and now I'm going to place my test charge in the exact same points. I had one here, and one here. And remember that this is a charge plus little lowercase q. Now what's going to happen to this positive charge Q? Since Q is positively charged and capital Q is negatively charged, they're going to be attractive, and thus pulling my test charge inward. No matter where my test charge is, it's going to be pointing inward. And so the electric field lines around a negative charge are always going to be pointing inward. Okay, so that takes care of direction. But we can also take care of magnitude. The number of field lines starting or ending on a positive or negative charge is proportional to the magnitude of the charge. So for example, if I have some charge Q here, I might have electric field lines that look like this. But if I have a charge 2Q, the force is twice, and so I'm going to have more lines. And thus 3Q would be something that looks like this. More electric field lines still. And you can imagine the larger Q is, the more field lines you're going to actually show. Another way to look at this is that the electric field is going to be stronger where the field lines are closer together. Now this gets useful when we start dealing with multiple charges, like in this case right here, something we call the electric dipole, or two equal charges, opposite sign. Okay, so we need to find, this may look complex at first, but it's really nothing more than vector addition at multiple points. Okay, so we're going to put our test charge anywhere, say right there. What's going to happen to that test charge due to Q1? Q1 is positively charged, so it's going to repel it, push it away. So I'm going to call that E1. But what's going to happen to that charge due to Q2? Well, Q2 is negatively charged. My test charge is positive. Therefore, it's going to attract. If I add the two, I'm going to get something that looks like this. In fact, let me recolor that and say that's my electric field E. And if I did the same thing at another point, say right there, and another one right there, then I can get a similar effect, a similar, vector addition. I'm trying to do 2 or 3 things at once. And so you can end up mapping out the electric field all around this electric dipole by taking any point and adding the 2 electric fields together at that point. You will not need to actually add them together. You just need to know that where these diagrams came from. Now, here's an interesting scenario. What if you have a charge of positive 2Q and a charge of negative Q here? Well, then the electric field around your charge Q is going to be much stronger. And so what you might have is something that looks like this. Oh, that didn't work well. It's got to be uniform. And then all of these are pointing towards the negative Q and away from positive 2Q. Why does it look like this? Because 2Q is much stronger, and so if you add the vectors together, they're going to have a more pronounced effect around 2Q. Okay, here's another good example of electric field lines. Here, this is a situation we're going to deal with multiple times over the next few chapters. Here you have 2 parallel plates, 2 conductors that are close to each other. But we're going to charge the left one up to a charge of positive Q and charge the right one to a charge of negative Q. Electric field always points away from the positive but towards the negative. So from positive to negative. I'll use that multiple times. And you'd end up with a situation that looks like this. In the middle, these are pretty much straight lines. But as you get towards the outside, they kind of curl around a little bit. We usually are going to look at a parallel plate that's somewhere in the middle, and so we won't have to worry about these rounded edges, but they are, if there is an edge, those rounded electric fields are there. They are important. So a quick summary of electric field lines. Field lines indicate the direction of the electric field or anywhere around a charge. The electric field itself being a field of influence on any other charges that might be out there. Oh, I need to point this out to you too. This is an important point. Let me do this. So let's say that you have a charge Q here, positive Q. Doesn't matter what the charge is. Electric field lines are pointing away. Any positive test charge positive Q will be pushed away. But if you have some test charge that is negative Q, well, remember that this push away is an electric force, and electric force is going to equal Q times the electric field. So if I have a negative Q here, Let me just rewrite it here. If I have a negative Q, then that means the electric force is going to be in the opposite direction of the electric field. So that's a very important point to note, that the electric field always points away from a positive but towards a negative. Any positive charges in the electric field will follow in the same direction as the electric field, but any negative charges will go in the opposite direction. Okay, so field lines indicate the direction of the field, and the field is always tangent to the line. And by that I mean if you have a positive charge negative here, at any one point, the electric field is going to be tangent to the line at that point. Tangent meaning parallel to that surface. Number 2, the magnitude of the field is proportional to the density of the lines. The more lines you have, the stronger the electric field is going to be. 3, the field lines start on positive and end on negative, going positive to negative. And again, the number of lines is proportional to the magnitude of the charge. Now, just to finish up our discussion on electric field lines, we need to talk about electric field lines and conductors. Now, this is interesting because it turns out that there are no electric fields within a conductor. Why? Well, shortest explanation is that if there is an electric field within a conductor, the charges within the conductor will move to cancel out those electric charges. Here's another way to look at it. So you have a charge Q, positive Q, in the center of a conductor. So it has an electric field that's radiating outwards. That means that inside the conductor it has an electric field that looks like this. Well, any positive charges that are in that electric field go along with the electric field, so they're pushed to the outside of the conductor, which is why you see the positives here on the outside. But any negative charges are pushed in the opposite direction. In other words, they're pulled towards the positive charge, meaning that the inside of the ring becomes negatively charged. So now all of a sudden you have positive charges on the outside of the conductor, negative on the inner side of the conductor. If you have a separation of charge, well, you have a positive on the outside, negative on the inside. Guess what that does? That creates an electric field within the conductor itself because of the separation of charges, and those electric fields cancel each other out. So you will not have electric fields within a conductor. The reason, this gives us some really interesting stuff, things to think about. For example, if you're in the middle of a thunderstorm inside of a car, you're relatively safe in a car. If you're in the middle of a thunderstorm and you have two choices of an isolated tree or a metal shed, logic would say, don't go to the metal shed because metal conducts electricity. It's that conduction that really makes the shed the safer place, because inside the metal shed you are not going to have an electric field. Therefore, you are going to be more protected inside the metal shed than you would be underneath an isolated tree. Just an interesting thought.